I know what you're wondering now. You're wondering when you can come back for seconds because this stuff is so good. Well, let's go to the second fundamental theorem of calculus. Let f be continuous on the closed interval a to b, and let capital F be an antiderivative of little f. In other words, capital F prime at x is going to equal little f of x for every single x in that closed interval. Then the second fundamental theorem of calculus guarantees us that the definite integral evaluated from a to b of f of t with respect to t is going to be capital F of b minus capital F of a. So it's going to be the antiderivative evaluated at the upper limit b minus the antiderivative evaluated at the lower limit a. And you might wonder, why do we have x's up there but we got this dummy variable t showing up again? And that's because we actually use the first fundamental theorem of calculus to prove this, so I'll let you look into that and see how that works. But anyway, so that's why we have that dummy variable t there. However, in reality, we could have x's here. I'm going to show you a few examples here where we actually use the second fundamental theorem of calculus and see how nice and easy it is. So in this first example, we're going to take the definite integral from 0 to 3 of x squared with respect to x. If you remember, this is a friend of ours from multiple videos where we actually did this with inscribed rectangles, circumscribed rectangles. We realized that this was on or above the x-axis, so it was actually equal to the area of the plane region, and we got 9 every time, exactly 9. So let's now solve this using the second fundamental theorem of calculus. So remember, what we want to do here is we want to find an antiderivative of x squared. So here's my little f of x is x squared. So capital F of x, what is an antiderivative of that? Well, it might be easier to say the derivative of what is x squared. Well, the derivative of x cubed is 3x squared, so that's close. But if I said x cubed over 3, that's the antiderivative. So remember, we have antiderivative theorems from before. This particular one, we can use the power rule, where we add 1 to the exponent and divide by that exponent, so it's x cubed over 3, and then normally we put plus c for any arbitrary constant for the family. However, in this case, all we care is that capital F is an antiderivative, so the easiest one to do would be where that constant is 0, and ultimately it doesn't matter if I put plus 5 in there. When I evaluate that, the plus 5s would end up going away because you'd have a plus 5 here and subtract a plus 5 there. So no matter what your constant is, it's going to go away anyway, so we'll just ignore the constant when it's a definite integral from a to b. So in this case, we're going to evaluate this from the lower limit of 0 to the upper limit of 3. And to do that, I'm just going, we can use a bracket here. Sometimes you just see a line there, but this is kind of shorthand notation so that we can end up finding this is your capital F of x here, an antiderivative. And what we're going to do is we're going to plug that upper limit in everywhere you see an x, so this ends up being 3 cubed over 3, minus f evaluated at the lower limit. We're going to plug that lower limit 0 in for x, and we're going to get 0 cubed over 3. Of course, that's 0, and we know that 3 cubed over 3 is exactly 9. So the same thing that we had every other time we did this one, we got 9 for our answer. And I know what you're wondering now, why in the world didn't we just use the second fundamental theorem of calculus, because this is so easy? Well, we didn't have it yet. So let's look at the next example. If I've got the definite integral from 0 to 5 of x cubed minus 1 with respect to x, so really we're just looking for an antiderivative, and then we're going to evaluate it from a to b. So once again, the integral of the sum is the sum of the integrals. The integral of the difference is the difference of the integrals. Those are from our antiderivative theorems. And then so really all we want to do is come up with an antiderivative. So the antiderivative of x cubed is x to the 4th divided by 4 for our power rule. And then minus the antiderivative of 1 is x, right? Because the derivative of x is 1. And I want to evaluate this from 0 to 5. So by doing that, I'm going to plug the 5 in for the upper limit everywhere there's an x. So this is 5 to the 4th divided by 4. Well, 5 to the 4th power, if you don't know that off the top of your head, I can split it up. That's 5 squared times 5 squared, which is 25 times 25, or 25 squared is 625 over 4 minus, and then I've got to plug a 5 in for this x as well, right? So I plug it in everywhere there's an x for the upper limit. So minus 5, I'm going to go ahead and make that minus 20 over 4 for the upper limit. Capital F of b is the upper limit here, and then minus the lower limit. When I plug 0 in here, I'm going to get 0 minus 0, which ends up being 0. So subtracting the lower limit didn't really do anything here. Didn't change it. But anyway, so 625 minus 20, since I had a common denominator, is 605 over 4. So the answer to this definite integral is 605 over 4. So let's look at one more example. And in this example, we got a little bit more involved thing here where we have the definite integral from 0 to 2 of x squared times the square root of x cubed plus 1 with respect to x. So there is no easy antiderivative that I can come up with using my antiderivative theorems. So what I really need to do is I need to remember what we did for tactics in previous sections and come up with substitution methods that might help with this. So the reality is, if I let u equal x cubed plus 1, then du is going to equal 3x squared dx. So when we did that before, we left the dx on the right side. Well, if you notice, I've got an x squared dx right here, and I've got an x squared dx right there. So what is that equivalent to? I can get that 3 to the other side, and I can replace that with du over 3. So this is going to be equivalent to, instead of du over 3, I'm going to put that 1/3 out in front. I'm going to have an antiderivative. Now, this antiderivative went from 0 to 2. I know in the previous video, I changed that lower limit from a 3 to a 9, but I shouldn't have done that because the t's were ranging from 3 to x squared, so not the u's. So I did not need to change that. It didn't end up mattering because the first fundamental theorem of calculus doesn't worry about what that constant is. So, but in this case, it would be wrong to write 0 to 2 here. So instead of doing that, I'm going to say this is equivalent to 1/3, and since I'm going to be in terms of u, I don't know to I don't know. Now, if you really wanted to know, I could plug in 0 for x and say that this is u equals 1, and I could plug in 2 in for x, and I could say that this is u equals 2 cubed plus 1 is 9. So the actual limits would be from 1 to 9 there if you leave it in terms of u. And what I'm going to do is I'm actually going to come back, figure out what the antiderivative is, put it back in terms of x, and then use the limits of integration that I know. So anyway, once again, the x squared and the dx is du over 3. So I'm going to have my du there, and I have my over 3 as 1/3 out in front. And then instead of the square root of x cubed plus 1, this is the square root of u, which I'm going to write as u to the 1/2 power. And once again, since I'm not evaluating anything yet, I'm going to just ignore what those upper and lower limits are in terms of u. So I'm going to give myself a little room. I'm going to come back here so that we can keep working. I'm going to go over here. So this is 1/3 the antiderivative of u to the 1/2 with respect to u from I don't know to I don't know. But anyway, so if I do this, this is going to be 1/3, and the antiderivative of that, I can use the power rule. So that's u to the 3/2 divided by 3/2. And we don't need the plus c, right? Things of that nature. So instead of dividing by 3/2, I can multiply by 2/3. And that ends up being 2/9. So this is equivalent to 2/9 u to the 3/2 power. Okay? Now, I'm going to come back to that, but what I'm going to want to do is I'm going to want to sub back. So we know that u was x cubed plus 1. So what I can really do is I can say this is 2/9 times, instead of u, it's x cubed plus 1 to the 3/2 power. And then what I'm going to do is I can evaluate it now from my lower limit to my upper limit. So I'm going to evaluate this thing from 0 to 2. Now if I do that, I'm going to go ahead and plug that in everywhere I see an x. This is the only place I see an x. So this is going to equal 2/9 times, instead of having 2/9 on there each time, I'm going to go ahead and leave that factored out in front. Anyway, plugging a 2 in here, I get 2 cubed plus 1 is 9 to the 3/2 power. Well, the denominator is the root, so that would be 9. Square root of 9 is 3. 3 cubed is 27, right? So anyway, 9 to the 3/2 power, I'll let you verify that, but I'm pretty sure that's 27. And then minus, if I plug in 0 here for x, 0 cubed plus 1 doesn't go away. It's 1 to the 3/2 power. Of course, square root of 1 is 1. 1 cubed is 1. So it's 27 minus 1. So this equals 2/9 times 26, which ends up being 52 over 9 for that definite integral. And just to verify what we could have done if we actually did change this over on the limits of integration here from the lower and upper limits, and I went ahead and I said, hey, when x is 0, u is 1, and when x is 2, u is 9, and I left it like that, and I had this. What I could have done is I could have evaluated this thing from 1 to 9. And if I do that, let's try it and make sure that we get the same exact answer of 52/9. If I did that and I plug in 9 for u, this would be 2/9 times the upper limit evaluated minus the lower limit, so I'm just going to plug it into that and use the distributive law. So the square root of 9 is 3, cubed is 27, and then minus, if I plug in 1 for that u, once again, 1 to the 3/2 power is 1, and if you notice, this ends up equaling the same exact answer there. Now you may have liked this better because you didn't have to substitute it back, which made it a little bit more awkward in our case, but you just have to be careful. If you change it over to use and leave it in use, you've got to change those limits of integration. So I'm okay with you doing it the green way here. However, just make sure that you are changing those limits of integration. But just to be safe, if you want to just do it in terms of u so you can figure out the antiderivative, substitute it back, then you can just keep the original limits of integration, and I think hopefully your plate is more than full now and you can go attack some problems.